Okay, let's start. So I just summarize the slope deflection equations for you on this. All right, are you ready? So be careful about the definitions. That's the first thing you need to note. So we have defined rigid body rotation angle. We have defined rigid body rotation angle connecting the deformed elements, the two endpoints of the deformed elements, and measuring from the original reference directions. That's called rigid body rotation angle. And there are two end angles, theta A and theta B, also defined with respect to the original orientations of the elements. And all of these are defined as positive if they are counterclockwise. And we have two end moments, MAB and MBA. So they are also defined as positive counterclockwise. So these definitions are used during the calculations. At the end of the calculations, when you go back to plotting the moment diagrams, you still have to follow the definition, the traditional definitions. So either you're doing coordinate definitions or you're defining according to the tensile site notations. So that's the first thing you need to notice on the definitions of these parameters. Now the second thing is the equations here. So two equations combined into one. So the sequence of the subindex is very important. So Mij is not equal to Mji. MAB is not equal to MBA. So this is the equation, slope deflection equations. So each and every one of them are defined. This is the fixed end moment. Now, fixed end moment is referring to these conditions. I have elements claimed on both sides. And what are the elements at the ends? And we are expecting to get these fixed end moment from the table. So no need to do further calculations on the fixed end moment. You just look up from the table. There are two cases I want you to remember, to memorize. The first case is uniformly distributed force. So if I have a uniform distributed loads applying, the length is L, and the two end moments here is WL squared over 12. So I want you to remember this. So if I see this loading like that, then the fixed end moment at this end will be positive WL squared over 12. The fixed end moment at the other end will be negative WL squared over 12. Okay, because this is clockwise. So that's UDL, uniform distributed loads. The other is a concentrate force at the midspan. So if I have a concentrate force at the midspan, then the end moments here is PL over 8. So these are the two cases I wish you to memorize. PL over 8, PL over 8. So as a result, the fixed end moment will be positive PL over 8. And on the other end will be negative PL over 8 for the fixed end moment. So in an exam, if I give you these two loading conditions, I will not give you any table. If I give you other loading conditions, then I'll provide table for you. Is that clear? Good? So remember these two cases. So for the remaining of this lectures, I'm going to give you more example to illustrate how we can use this slope deflection equation. Okay, let's take a look at this structure. So identify degrees of indeterminacy. So clamp, and then roller support. So you know very clearly, very straightforward, this is a 4-degree indeterminate structure, 4 degree. So that means that in addition to equilibriums, you need to provide 4 additional equations. So if you go for compatibility or if you go for the energy approach, you need to come out with the 4 equations simultaneously and then solve for the 4 unknowns, right? So that's what you need to do. So I want to use the slope deflections to solve this problem now. The procedure goes like this. First, you identify degrees of freedom. You identify degrees of freedom, and you set up the slope deflection equation for each element that you identify. And then you exercise so-called joint equilibriums, and then solve for the unknown degrees of freedoms. So let me show that to you. So for this structure, I decided to model the structure using 2 elements, AB and BC. So A is a clamp end, so I don't expect to see any rotation angle. B can rotate. C cannot rotate. So I can imagine, if you can, plot out the deformed shapes. So this is the deformed shape. I call this node A, node B, and node C. So identify degrees of freedoms. Not difficult to see that theta A is going to be equal to 0. Theta B not equal to 0. Theta C equal to 0. So I'm going to model the structure like that and start to get into elements. Take this out, 1 element. This is node A. This is node B. And I also take this out. So node B and node C. So they're connecting at node B. So I'm trying to zoom in at node B. There. So here's the B. So in a way, I'm doing this. I'm modeling the structure like this here. Here, I call it element AB. Here, and here, I call it element BC. And the connection point there, I single out, call it node B there. OK, so let me put down. This is MAB. This is MBA. N moments for element AB. This is MBC, and this is MCB. Okay, I'm just putting down the definitions. So I need to set up the slope deflection equation for each one of the elements. So knowing that theta A is equal to 0, theta B is not equal to 0. So let me set up the slope deflection equation for this element first. So for AB elements, MAB 2EI. Oh, I haven't given you EI. EI is a constant. 2EI over L. L is 8 meters. 2 theta A. Theta A is equal to 0. 1 theta B. Theta B is not known. And then minus 3 times rigid body rotation angle. You connect the deformed shape. Of course, you know that that line is horizontal, so no rigid body rotation angle. That's it. How about fixed end moment? Now, there's no loads. No loads. So fixed end moment is caused by the external loads or external loads mainly. So no fixed end moment. So that's MAB. Similarly, MBA is 2EI over L, 2 times theta B. Theta B is not known. 1 times theta A is equal to 0. Minus 3 times rigid body rotations, 0. No fixed end moment. OK, so that's element AB. BC. So we can do the similar equations for BC. MBC is 2EI over L, which is 6 meters. 2 times theta B, 1 times theta C equal to 0, minus 3 times rigid body rotation angle. So you connect the deformed shape. There's no rigid body rotations. So again, rigid body rotation is equal to 0. So that's it. But we do have fixed end moments. Because we have a loading acting on BC. So what is a fixed end moment? So we go to the textbook and look this up. So if this is W, then the textbook tell you that this is WL squared over 30. And this is WL squared over 20. OK, so fixed end moment for BC is WL squared over 30. W is 6. So 6 times 6 squared over 30. So which is 7.2. Okay. So far, so good. I'm just copying whatever I wrote there, just trying to implement. All right, so MBC. Now, MCB is 2EI over L, 6. 2 times theta C, 0. 1 times theta B, here. Rigid body rotation, 0. Fixed end moment. So fixed end moment is negative WL squared over 20. So negative WL squared over 20. So this is 10.8. So far, so good? OK. Now, I go to note B now. Action reactions. This is MBA. Action reactions, MBC. I go to node B, exercise my action reactions, and they should have a moment equilibrium there. So go to joint B. Moment equilibriums. So I take this moment and this moment, add up. Force that goes to 0. You can see that the only unknown from this summations is theta b. OK, so I get theta b out of these equations. Is that clear? It's quite clever, huh? So you get theta b now. Negative, what does that mean? Negatives means that it's clockwise. So rotation at B is clockwise because it's negative. OK, cool? Now, after that, then things become very clear what you need to do. So you just take this value, substitute it here, 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 and here. Then you get the end moments. All right, so let's get the solution. This OK, you see how quickly we can come up with a solution. There's only one unknown. Once this unknown is found, then all the solution comes out. So in comparison, you can see that if you go for energy approach, least square approach, Castigliano theory, least square approach, or you go for compatibility, you only need to generate like 4 equations or 3 equations if you take away the actual force. At least 3 equations to solve this. But for this case, if you go for slope deflection equations, there's only one unknown. You don't have to solve for the simultaneous equations. Right? It's very straightforward calculations. So is it all right? Do you have any questions? So let me summarize the steps for you, what you need to do. So first is identify degrees of freedoms. That is, you need to identify which are 0, which are not 0. You need to also provide on the way how you want to model your structures. You want to model the structure, call this one element, the other elements, or you want to split into even finer 1 element, 2 elements. It's up to you. But you need to provide such a modeling and then identify degrees of freedoms. So by that, I mean degrees of freedoms means rotation angles or rigid body or deflections. Sometimes deflection will get into your pictures. Later on, I'll show you. Second is you set up slope deflection equations for each element. So this is what I did here. Set up slope deflection equation for each element. Step 2. Step 3, joint equilibrium. Joint equilibrium. Then use that, you'll be able to solve for the unknown, or degrees of freedoms. And after that, you just substitute this back in there. So you get the end moments. That's step number 4, more like a finishing up. Okay? So very, very systematic approach. So let me show you how you can finish up. I expect you to do that during the exam, of course. You cannot just stop here. You have to complete your analysis. OK, let's complete the analysis. Maybe I can do it here. All right, so maybe I come over here to do it. MAB is minus 1.54. MBA minus and MBC plus MCB minus so you put down the end moments and then start to do the equilibrium calculations on each one of them. So don't forget there's a loading here. Do not forget. There's a triangle loading here. So you come over here, do equilibriums. You'll find out that you need a shear force to balance this. Come over here, do moment equilibriums. You find a shear force. And you do a force equilibriums. This shear force has to be balanced. So you have the shear force there as well. And then you go to this element and then do equilibrium calculations. You come over here, take moments. You find out this force. And then this force using force equilibriums. OK? So do it on B, action reactions, action reactions, action reactions. Then you can find out the support force there. This plus that. OK, done. Your analysis is complete. Next is plotting the shear force bending moment diagrams. So shear force diagrams. goes down, goes up. And then you have a distributed force, linear downward. So your shear stress goes like this. It goes up. So this is 1363. All right, so that's the shear force diagrams. I expect you to do all the way to shear force and bending moments. And bending moment, you will be asked to plot at the tensile side notations. So with the bending moment given here, can you do a bending moment plotting at the tensile side? So let me show you the plot. This is bending moment, tensile side. So you look like this. So this is going to be the tensile side. This is tensile side. Here's a tensile side, and here's a tensile side. All right, so it goes like this. All right, that's complete. That's the tensile side moment distributions. Okay, any questions? Let me stop for 2 minutes. Think about it, whether you can get this very quickly now. So the rest of the calculations follow very similar. If you understand this concept, it's going to be a little bit easy for you. This is too low. All right, any questions? So let me just show you some variations. So I'm hoping that everybody should be able to do this after having the internal forces obtained. So let's see some variations. All right. So here, slight variations. So you see that there's a free end. So can you draw the deformation shape? So let's try that. So can you imagine that this structure might be deforming into this shape? Now, and the actual deformation shape depends on the material property as well as the loading conditions. So I can only guess. It might deflect into the shape. But whether this point eventually goes down or goes up, or this angle is going to be clockwise or counterclockwise, so is that angles, I really don't know. I have to get that until the solution comes out and tell me. But if I can come out with such a deformation shapes, and I can start to model my structure in the slope deflection way. So I call this A, B, C, and D, with the intentions to model this using 1 element, 2 element, and 3 elements. So imagine the degrees of freedoms now. How many degrees of freedoms that you are going to have if you start to model your structure like that? So you're going to see one rotation angle. So rotation angle is equal to 0 there. Rotation angle is not equal to 0 there. Rotation angle is not equal to 0 there. And the rotation angle is not equal to 0. And then there's a deflections. So that deflections is there, but you don't know. So, so how many degrees of freedoms or unknowns that you can come up with if you want to model your structure like that? So you see 1, 2, 3, 4. 4. So 4 unknowns, so you're expecting 4 equations. But if you take a look at the structure, you quickly identify that this structure is a 2-degree indeterminate structure. So if you just go for the energy approach, the least work principles, you only need 2 equations. So it's a 2 versus 4. So which approach you will adopt? Of course, the energy approach, right? It makes more sense, right? Why do you want to go for the 4 unknown cases versus the 2 unknown cases, which is supposed to be easier? Yeah, so it's going to be case dependent. Now, each problem might require different solutions or different approach. All right, so that is a judgment you need to make sometimes, which methods you want to use before you get into analysis. Don't just go right to it. You have to stand back and then take a look at that. However, we also notice this. If you look at the structure carefully, if these 2 informations are not very critical to you, you say that I only want to get the internal force. I want to get the shear force. I want to get the bending moment. I don't really care about deformations, OK? If these 2 are not your concern, can you see that this side of the structures, this part of the structures actually is already known? Can you see that? If I cut a cross-section anywhere on this segment, it's already known. You don't have to go through the whole calculations. Can you see that? You can see that, right? If I do a cross-section cut there, I know the shear force is going to be 30 upward, and bending moment is going to be this way, 30 times distance. So they are already known. So if that is what you want, you don't care about this two, if that is all you want, you don't need to analyze this part. And you don't need to analyze these two unknowns. OK? So what do I mean by that? Let me show you. It really depends on what you are asked to do. So what you need to do is I cut the structure into two parts. One part is I cut it from here. So this is the this is the right-hand side. This is the left-hand side. I cut it just to the right of C. So I have an external force of 30 there. And I know I'm going to need a shear force of 30 upward to balance that. And I know I'm going to need a bending moment of 30 times 4, 120, to balance that. That's what I mean. I know the shear force and bending moment inside this component. No problem. All right, so if that is the case, I can just take this away. Forget about it. That part is already known, solved. Action reactions tell me that I should have 120 there, and I should have a force of 30 there. OK. So you just forget about this part and just look at this part. Then how many unknowns or how many degrees of freedom do you have? So you have 1 and 2. So you have 2 degrees of freedoms. If you realize that you don't really care about these 2 values. Cool? OK, so let's go. This is A, B, and C. I'm going to do the same procedure. So set up AB. M, AB, 2EI over L, 6. 2 times theta A, 0. 1 times theta B, unknown. Rigid body rotation, 0. Fixed end moment, 0. That's it. MBA, 2EI over L. 2 times theta B, 1 times theta A equal to 0. Rigid body rotations equal to 0. That's it. That's element AB. And BC. So MBC, 2EI over L, which is 9. 2 times theta B, 1 times theta C. No rigid body rotations. We do have a fixed end moment because there's a loading there. So fixed end moment for UDL is WL squared over 12. So you're expecting to see a fixed end moment on both sides. So the fixed end moment is 67.5. So this is coming from WL squared over 12. OK, so that's MBC. MCB, 2EI over L, 2 theta C, 1 theta B. No rigid body rotations. And fixed end moment is minus 67.5. All right, that's it. We only have 2 elements. Now we do the joint equilibriums. So we go to joint B. The joint equilibriums at B is MBA plus MBC equal to 0. So that's one equation, and you go to joint C. So what is happening at joint C? Let's take a look. Blow it up. This is B, this is C, and this is joint C. There. So at joint C, you have MCB, action reactions. And you have this 120 coming from the right-hand side. So that is what happened at joint C. All right, so the equation is MCB plus 120 equal to 0. So you pick this equations, sum up with this equations, put it here. And then you use this equations and then put it here. So you have two equations, and then we say that we have two unknowns, which are theta b and theta c. So here are your simultaneous equations. So just solve the simultaneous equations. OK, done. Theta b and theta c are found. They are negative, indicating they are doing clockwise. So clockwise. So this is clockwise. This is counterclockwise. So, but the results tell you that both of them are clockwise. So we need to modify our deformed shape. So it should be a clockwise rotations. So this is a clockwise rotations. So going up, going down. So there must be somewhere in between that is doing this. So that will be your deformed shape. This is not straight line, by the way. There's a bending moment, so it's not straight line. All right, so that's a deformed shape. So you take this two value, and then go back to the slope deflection equations, substitute it in. Then you have all the end moments. All right, so you have all the end moments calculated now. So the rest of the calculation is just going to elements level, doing equilibriums, getting shear force, and then you can plot the shear force bending moment diagrams from there. OK, let me stop for 2 minutes. You can discuss and ask me questions. Okay, any question? All right, so now let me come back here and explain to you why we need to define the bending moment and then all the rotation angle, like following a certain notations. So you can see that the reason is quite clear why we have that. It's because when we do equilibriums, we are doing at the joint level. So if you follow the original definitions, sometimes this is positive, sometimes that is positive, it's very confusing. All right. But if you follow the notations defined in this chapter, then you see that all the joint equilibriums are just plus and plus. You don't need to worry about whether this is positive, that is positive, and then you confuse yourself. So everything is summation. So just remember that. But that is only used to help you to calculate. But once you get the bending moments, when you plot the moment diagrams, you still need to follow the definitions of the moment diagrams. All right. I can repeat many times, but if you fall asleep, nobody can help you. All right. Now let's introduce settlements into the analysis. So I have a clamp beam, and I support it inside the beams. I support it by 2 roller support, UDL, and concentrate force. Also, one of the roller support has a settlement of 25 millimeter downward. So you're asked to analyze this structure. So I decided to use 1 element, 2 elements, 3 elements, 3 elements to analyze. So degrees of freedoms, rotation angle 1, rotation angle 2. That's it, 2 rotation angle. So draw the deformation shapes. So imagine that this is going to be rotated, but goes down this way. So it's going to be something like this. Hey guys, any questions? Okay, go. Now, obviously, this connecting to that, there's no rigid body rotations for AB. For BC, there's a rigid body rotations once you connect to two endpoints. So here is your rigid body rotation angle. And it's a clockwise rotation. So the rigid body rotation angle for BC is going to be negative of this divided by the length. So you'll be expecting to see a rigid body rotation angle comes out. BC is going to be negative (25 millimeter) over the length of 8. So that's a rigid body rotation angle. Same thing, if you connect CD, the deformed shape CD, here is your rigid body rotation angle. And that is counterclockwise. So you're going to see positive rigid body rotation angle. All right. If you can have that, then you are almost sure. Fixed end moment. Let's figure out the fixed end moment first. So there will be fixed end moment here. Fixed end moment, fixed end moment, fixed end moment, fixed end moment, and fixed end moment. They are everywhere. So put down the fixed end moments. AB is a UDL WL square over 12. So it's 12 L square over 12. Fixed end moment BA is going to be negative of this. Fixed end moment BC, same thing. Fixed end moment CB, and this CD. Concentrate force at the midspan, PL over 8, PL over 8. Another one on the other side. Okay, these are the preparations to get you started. So now we get into elements one by one. Element AB. So MAB is 2EI over L, 2 theta A, 1 theta B, no rigid body rotations, fixed end moment. That's the first equation. Second, BA 2EI over L, 2 theta B, 1 theta A equal to 0, no rigid body rotations, fixed end moment. All right. So that's it, AB. And then BC. So BC 2EI over L 2 theta B 1 theta C minus 3 times rigid body rotations minus 3 times rigid body rotations. So it's plus right. And fixed end moments BC. All right. And CB 2 theta C 1 theta B minus 3 times rigid body rotations, the same thing. Right? I'm only using that equation. That is the only equations I know. CD theta D is equal to 0 and minus 3 times rigid body rotations. And fixed end moments. All right. Last. All right, done. Slope deflection equations. You guys are getting bored? Maybe I can move on faster? No? I am getting bored. I'm writing the same equations like 10 times, 12 times. So is there any place that you don't quite follow or understand? Okay, next is the joint equilibriums. So, two joints. Yes?
Why the deflection line at point C is sum?
Oh, that's a settlement.
It's
It's
a settlement.
a settlement. Settlement. You know what settlement is? Yeah, it's a settlement. Because ground is soft, so it's settled. Yes? It's from here. That's the formula I asked you to remember. So if you have a UDL of W, uniform distributed load of W, then the two end moments will be WL squared over 12. All right? Cool. Now, the rest of the calculation is joint equilibrium. Joint equilibriums. Let's go. So you go to joint B, and equilibriums is MBA plus MBC equal to 0. So you need to pick up this equations and this equations, put it here and here. And then you go to joint C. joint equilibriums is mCb plus mCd equal to 0. So you come to this and this and put it here. So there are only two unknown, theta b and theta c. Simultaneous equations, perfect. You get theta b, theta c. Okay. The rest of the calculations is just plug the degrees of freedom back into the slope deflection equations. So you get that, and then start to plug it in. Then you have the end moments, and you go for elements equilibriums. You get shear forces. So let me just give you the final answer. All right, these are the final answer after I plotted in the two rotation angle into the slope deflection equations. Very, very exciting. Yeah. Very exciting, right? The steps are kind of repetitive. Huh? You see what? You see the excitement?
No, I see the help.
All right. So any questions about this example? So next, we want to get into two-dimensional structures and also some structures coming in without with deflections, displacements. So before I do that, let me show you one slide. Let's say I have a structure. So I have loading. So I define nodes. All right. So look at this structure with loading, and identify degrees of freedoms. I have 1 rotation, 2 rotations, so I should have 2 degrees of freedom. However, similar to the previous example, if I identify some part which I either know structurally, or I know that, for instance, the moment there is equal to 0, then I can utilize that conditions to simplify my calculations. So let me show you how you can do that. So this is moment BC. This is moment CB. There's a rotation angle here called theta B and theta C. So I know that this MCB is equal to 0 because there's no external force bending moment there, so MCB is equal to 0. So I'm going to utilize these conditions to simplify it. So I set up. I just want to put it a general case. That's MBC. And put down MCB. All right. So if I know that I don't have any moment applies there, so MCB should be equal to 0. So I force this goes to 0. So I can express theta C as a function of theta B and phi BC and the rest. So I can get theta C comes out. I'm just forcing the M moments to go to 0 if I know that there's no external moment there. And then I can solve for theta C as a function of the rest of the parameters like that. And then I can substitute theta C in here, eliminate theta C from getting into the equations. So I will have a modified MBC. Substituting here, there. So the modified equation is like this. So that's a modified equations where you only have one unknown or one rotation angles theta B in it. Okay, so if you see this, if you see these conditions, you can utilize this and try to eliminate theta C from getting into your calculation completely. All right? So yes, there's a theta C, but you have to use that to calculate because you can see that MBC does not contain theta C. So if that is the case, then you exercise joint equilibrium there, then the only unknowns will be theta b. There will be no theta c whatsoever. That is assuming that you can memorize these equations. But if you cannot memorize this equation, it's fine because it's quite easy to get. You only force this goes to 0 and then try to get theta c, and then that's it, right? It's not a very difficult test to do. Okay, but there's one factors I want you to remember. We'll come back to this factor in the next chapter. This factor of 3 is very important. Compared to, now this is referring to theta b. This is theta b. Compared to the original equations, which is a factor of 4 for theta b. So original equation have a factor of 4 EI over L for theta b, but the modified equation have a factor of 3 EI over L for theta b. So it's a 4 versus 3 ratio. So that becomes very important when we go to the next chapter called moment distributions. So you don't need to remember these equations, but just take notes of this 4 versus 3 ratio, because we're going to come back to that later on in the last chapter. Okay, I don't have time for another example, so let's come back on Friday. Just a reminder for those groups who have not submitted your problems to me, please do so as soon as possible.